Well, thank you. I'd like to thank the organizers for such an ambitious, is this working? Okay. Such an ambitious conference. And like most modern lecture halls, this has no clock. So I have my phone though. All right, so you've seen many instances where simplicity may be used to justify axioms, but this usually happens after the fact. And so a natural question is whether philosophical notions or notions of simplicity can help inform a process underway. And I would like to claim that that's possibly happening now, though it's like a story and the cliffhanger is looming and we don't know which way it's going to happen. All right, so the mathematical story of infinity, that's what set theory is all about, begins modestly with the empty set. Okay? And then we define the transfinite numbers, the ordinals. The empty set is the number 0. The set whose only member is the empty set is the number 1. There's 2. Abstractly, any ordinal is just a set of all ordinals which are smaller than it. And to get the next largest ordinal, you just do the obvious thing. So if alpha is an ordinal, you take alpha together, that's what that means, together with the singleton set alpha, and that's the next largest ordinal. So these go into the infinite. The finite ordinals are the natural numbers. So we can now unravel the universe of sets. So I have to introduce the power set of a set, P of x, and that's just all subsets of the given set. Okay, so the cumulative hierarchy of sets breaks down the universe by induction on the ordinal alpha. V0, the simplest part, is just the empty set. At the successor, we just take the power set. So, oops, sorry. So having defined V alpha, we define V alpha plus 1 by just taking the power set. If alpha is a limit, we just put together everything we've already defined. And it's a consequence of the axioms of set theory that every set belongs to a V alpha for some ordinal alpha. So there it is, the universe of sets. All right, let's look at the first few stages. V3 has 4 elements. Whoops. V4 has 16 elements. V5 has 65,536 elements. V1000 has a lot of elements. Omega denotes the least infinite ordinal. It's a set of all finite ordinals. Remember, every ordinal is a set of all smaller ordinals. Omega is the first ordinal that can't be reached by adding 1. V omega, the corresponding fragment of the universe of sets, is infinite, and it's the set of all hereditarily finite sets. So V omega is really just the natural numbers with plus and times. It's another representation of that. So though number theorists don't like to admit it, they're studying this structure. And this is in many ways an easier structure to deal with. If you don't have to code because everything is naturally there. It is the existence of V omega that distinguishes set theory from number theory. It's having that infinite set. Okay, so the original principles, those are the ZFC axioms of set theory, are naturally expanded by additional principles which assert the existence of very large infinite sets. So we're trying to repeat the transition from number theory to set theory is bringing in infinity, but maybe there are many other infinities one could imagine. These principles are called large cardinal axioms. So I'm going to show you some. This is the short version. So as we go down, the strength is increasing. Measurable cardinals, strong cardinals, my favorite, wooden cardinals. Now, I have to talk about them later on. It's not that I'm trying to promote them. And then super strong, and then reaching into the higher reaches, super compact cardinals, extendable cardinals. Now imagination for names starts to fade. Huge cardinals, omega huge cardinals. It's a vast hierarchy. Now, I should point out that every time you increase in strength, you increase the risk of there being a contradiction. So one view could be, this is a house of cards. And as we move to higher and higher notions of infinity, we're piling up more and more cards, more likely that the structure could collapse. So these could all be contradictory. In fact, at times, various people have thought they could show that there were no measurable cardinals. Now, you could say set theory or set theory in the context of large cardinals has no relevance. Well, that may well be true, but each one of these axioms is falsifiable, and so makes a prediction about the world. And that prediction is they won't be falsified. Now, whether or not you regard that as a meaningful statement, that is a prediction about the world. And how can you account for those predictions if they stand the test of time? If you're going to disregard all the notions. All right, that's my only bit of sales for set theory. All right, so those are the large cardinals. All right, so the continuum hypothesis, one of the most famous problems in set theory. So Cantor showed when he founded set theory that if you look at the set of natural numbers and the set of real numbers, they do not have the same cardinality. There's no way of doing a one-to-one matching between the two sets. The infinity of the natural numbers is the smallest infinity. It's the same as the infinity of v omega. The infinity of the real numbers is the infinity of v omega plus 1. All right, so we have these two infinities, but the question is the infinity of the real numbers the next largest infinity? Cantor's theorem shows that infinity comes in different sizes. So the continuum hypothesis asserts that the infinity of the real numbers is the next largest infinity. But you can restate it simply as I've stated it here. The continuum hypothesis simply asserts that if you have an infinite set of real numbers, then either it has the same cardinality as the natural numbers, or it has the same cardinality as all of the real numbers. There's no infinity in between. Where does this statement live? Whoops. We'll postpone that. What about this problem? By the middle 1900s, so Hilbert put this as the #1 problem on his famous list of 23 questions, or however many questions there were. By the middle of the 20th century, arguably this had become one of the most famous problems in mathematics. Okay, Gödel showed that it's consistent with the axioms of set theory that the continuum hypothesis is true. And then in a landmark development in the early 60s, Cohen showed that it's consistent with the axioms of set theory that the continuum hypothesis is false. Rephrased, you can't solve the problem. Has no answer on the basis of the axioms of set theory. The continuum hypothesis is a statement about v omega plus 2, so we have run into a problem right down at the bottom. So this makes trying to understand the universe of sets a bit of a problem. This is an infinitesimal fragment of the universe of sets. All right, so I have to say a little bit about Cohen's method. If M is a universe of set theory, so that's a structure in which all the axioms hold, then M contains blueprints for virtual universes which extend M. These blueprints can be constructed and analyzed from within M. That was Cohen's innovation. If M is countable, then every blueprint constructed within M can be realized as a genuine extension of M. Cohen proved that every universe M contains a blueprint for an extension in which the continuum hypothesis is false. So if you can build a structure in which all the axioms of set theory hold, you can build one in which all the axioms hold and the continuum hypothesis is false. In fact, Cohen's method also shows that every universe contains a blueprint for an extension in which the continuum hypothesis is true. Obviously, that's not how Cohen did it, but Gödel did it, showed the relative consistency of the continuum hypothesis, but Cohen's method can be used to do that as well. So we have a serious problem. And the problem is much worse when you penetrate into the details of Cohen's method. Because remember, we had those new principles, those large cardinal axioms. And you might hope that there lay the solution to the continuum problem. But Cohen's method doesn't affect the existence of very large infinite sets. So you're not going to use the higher infinities directly to solve the continuum problem. All right, so we have an issue. We have to deal with it. So the first attempt would be to introduce a multiverse. All right, so this is the generic multiverse. It's just a conception. If W is a universe of the generic multiverse, then this is the closure properties that define the generic multiverse. Then for each Cohen blueprint from within W, there's an extension of W in the generic multiverse that realizes that blueprint. So we're trying to form a smallest collection of universes starting from an initial universe. We have to be able to realize Cohen blueprints. But as we do that, we may encounter universes that themselves are extensions of a sub-universe by a blueprint within that universe. Then we have to put that into the generic multiverse as well. So that's an informal conception. So here's the generic multiverse truth. This is the vision statement for the position. We'll say that a statement is a generic multiverse truth if it holds in each universe of the generic multiverse. These are the universal laws this view would hold of set theory. These are those statements that Cohen's method cannot affect. And maybe that's all we can do. If we have lots of large cardinals, then that's a generic multiverse truth. It will persist across the generic multiverse. Now, whenever you try to do this seriously, you instantly raise a question, well, wait a minute, where is this generic multiverse being constructed? The universe has all sets. What are these objects? So you would like to show that this vision or this view isn't sensitive to that, and it turns out it's not at all sensitive to that. And the reason is these laws can be identified uniformly within each universe of the generic multiverse. So it doesn't really matter whether you view it as a generic multiverse or not. You just have a collection of sentences that you're interested in. So the retreat of going to the generic multiverse would be like the retreat some physicists might take in introducing, the physicists dream that they could compute the fundamental constants or the dimensionless constants from first principles. Well, maybe that's not possible. So maybe you just end up with a multiverse. Same thing. Computing a dimensionless constant is like trying to settle the continuum hypothesis. Maybe we just can't do it. So in this generic multiverse version of truth or view of truth, Cohen's method cannot be used to show that something can't be answered. But the price you pay for that is you relegate the continuum hypothesis into the position of being neither true nor false. All right. Now, in analyzing the generic multiverse view, one is led to something called the omega conjecture, which I'm not going to define. The context is a proper class of Woodin cardinals. One reason I had to introduce them. If you assume the omega conjecture, then from the universal laws of V omega plus 2, those are the sentences of V omega plus 2 that hold throughout the generic multiverse, one can compute the universal laws for V omega plus 3, or V omega plus 1,000, or V sub delta, where delta is the least huge cardinal. And one can prove abstractly, you can do it for any V delta, where delta is the least instance of any large cardinal notion, which is correctly specified simply by the existence of some V alpha within which that notion holds of delta, no matter how strong that notion is. Well, this is saying that the cumulative hierarchy in some conceptual sense has collapsed, and it's collapsing down to V omega plus 2. And it's even worse. These laws are actually definable in V delta plus 1, where delta is the least Woodin cardinal. You don't even need the whole universe of sets. So the laws are very complicated. From the point of view of the universal laws, the cumulative hierarchy collapses. And moreover, you only need a fixed stage of any universe of the generic multiverse to actually define what those laws are. This just can't possibly be right. This is too much simplicity. All right, now, for the logicians in the audience, this almost looks like a contradiction. Why can't you run Tarski's proof and just diagonalize out immediately? And the reason is something very subtle happens. Though these laws are definable in this fragment of the universe, the definition changes. It involves an integer parameter. It's not uniformly definable. All right, that's a technical aside, and I'll say nothing more about it. Okay, too much simplicity. So either the omega conjecture is false, or the generic multiverse approach is not an option. Okay, so we have to retreat. Okay, so there's another attempt one might try. Let's refine the concept of set. All right, so if you have a set X, the definable power set of X, P-def of X, is a set of all subsets of X, which are logically definable in the structure X together with a membership relation with parameters from X. It doesn't really matter the details here, it's just some simpler notion. So it's the collection of all simple subsets of X as opposed to P of X, which is a collection of all subsets of X. All right, so recall the cumulative hierarchy. It was generated by induction by iterating the power set operation. At a successor step, we took all the power set of what we had, and at limit stages, we just took the union, and we got all sets this way. So let's just replace the power set by the definable power set. And that's Gödel's constructible universe L. So it looks very much the same, except at that key step when we go from the alpha stage to the alpha plus 1 stage, we just take the definable power set. And at limit stages, we still take unions. And then L, as opposed to V, is the class of all sets that belong to an L alpha for some alpha. So this comes within an axiom, V equals L. Why don't we just add to the axioms of set theory this axiom? Suppose X is a set, then X is an L. It's a great axiom. Gödel showed that if you assume V equals L, then the continuum hypothesis holds. That's how he showed the relative consistency of the continuum hypothesis. I'm sorry?
The previous slide just for another moment and tell us the difference between
The previous slide, what? I'm sorry, I just can't hear.
Thank you very much.
Okay. Okay? V to L, we change the power set, we replace the power set by the definable power set. That's the only change. Okay? We get the axiom, we just assert, though we can't necessarily justify it, that every set is generated this way. Gödel showed that if you assume V is equal to L, then the continuum hypothesis holds. Interestingly, the definition of L does not require the axiom of choice, and if you assume V is equal to L, you get the axiom of choice, and that's how Gödel showed the axiom of choice was also relatively consistent. All right, what about the generic multiverse? Well, if you have a Cohen blueprint for V is equal to L, then the axiom V is equal to L must hold, and the blueprint is trivial. Restated in terms of the generic multiverse, if you assume V is equal to L, then V is the minimum universe of the generic multiverse. Okay, so this is looking better and better. Obviously, something's going to change, or I wouldn't be talking about it. What about large cardinals? Well, Scott showed around 1960, before this result was before Cohen, assume V equals L, then there are no measurable cardinals. The modern view is that assume V equals L, there are no genuine large cardinals. This is, again, too much simplicity. L's too small. It provides a robust conception of sets, but it throws out too many sets. So the corollary, the meta-corollary, is the axiom V equals L is false. It contradicts the founding principles of of set theory, which is kind of an expansionist doctrine. Solution is obvious. We want to construct enlargements of L in which large cardinals can exist. But how should we do this? Well, we try to use the large cardinals themselves to expand the definable power set. We got L by using the definable power set. We get V by using the full power set. We want an intermediate notion. The definable power set isn't giving us enough sets. Full power set maybe is giving us too many sets. Okay, so this seems quite reasonable, but if we're using the large cardinals to expand the definable power set, we better know all of the large cardinals, or we won't know that we've done an ultimate expansion. So this statement here just seemed obvious 5 years ago. There can be no ultimate enlargement since the construction would require identifying all notions of infinity. You can't do that. So with every enlargement, there's a generalization of Scott's theorem. However you define the enlargement, you won't have reached some higher infinity beyond that. So the program to understand V through enlargements of L can never succeed. That's kind of discouraging. This picture must be wrong. Or we have to go to attempt 3. It is wrong, possibly. Something completely unexpected happens. The enlargement of L for exactly one supercompact cardinal, no more, no less, is provably the ultimate enlargement of L. And this explains why the whole program was stuck for so long. So trying to do the enlargement for a supercompact cardinals has long been a key question. But this says you have to target exactly one supercompact or you're doomed to failure. Well, if you're going to try to advance inner model theory, advance the program, you just don't want to do one supercompact, you're tempted to do 2 or 3 or do huge cardinals. You can't do that. All right, so there's a very good candidate for the resulting axiom V is equal to ultimate L that one can identify now, even though we don't know how to construct this enlargement. That's this cliffhanger. The reason for doing this is that one can then analyze consequences of the axiom, and maybe that will help one do the enlargement, or in the darker future, refute the whole program altogether. All right, so what can we prove now? These are consequences of the specific candidate for the axiom V is ultimate L. The continuum hypothesis holds. The omega conjecture holds. Remember, the omega conjecture was the conjecture that basically, I claim, ruled out the generic multiverse view. We don't know whether the omega conjecture is true. We know it's consistently true. We don't know if it's consistently false. Cohen's method can't affect the omega conjecture. Okay, so that's interesting. L had this very nice property that it was the minimum universe of the generic multiverse generated by L. That's a consequence of V is ultimate L. So we're replicating some of the consequences of L, and so this seems promising. Okay, so now I view myself as a mathematician. I have to end with some specific statements. I'm not going to explain them. I'm just going to try to give you the feel for what this axiom is. Here's a candidate axiom. So this is a small, whoops. Maybe a higher power is trying to warn me. This is the small print. This is the axiom for V is ultimate L. There's a strong cardinal, which is a limit of Woodin cardinals. I'd like to put supercompact there, but we don't know it's consistent. And then this is the technical statement. If you have a sigma 3 sentence that holds in V, there's a universally bare set, blah, blah, blah. This can be defined in a first-year graduate course. If you put in all the relevant definitions, it wouldn't expand by that much. Hod was introduced by Gödel. This is the relativization of L to A and R. What's a universally bare set? Well, I can define that. A universally bare set of real numbers is a set of real numbers whose continuous pre-images in any topological space has a property of bare in that space. That's a fundamental notion in analysis. Sigma 3 is a level of complexity of sentences, and so forth. In fact, the hardest thing to define on this list would be Woodin cardinals, but I could just subsume that into a stronger theory. All right, but there's something missing here. How could you hope to show that this is an ultimate axiom? We need some conjecture and reasons why that conjecture would imply that this is the ultimate L. So this is the conjecture. It's a perfectly precise conjecture. I'm not going to define all the terms, but there it is. If you have an extendable cardinal, that was on my list, then there's a transitive class N. N is a suitable extender model. That's the notion. For delta supercompact, they're supercompact. I'm requiring N is contained in HOD. That's not really essential. Here's the essential bit, that the axiom I am ultimate L holds an N. Notice that in this statement, there are no huge cardinals, there are no omega huge cardinals. I haven't used much of the large cardinal hierarchy at all. This conjecture just talks about really supercompact. But one can show that if this conjecture is true, that this model N that you build is universal for large cardinal axioms. It really is an ultimate version of L. No, it can be no version of Scott's theorem. If this conjecture is true, this axiom is compatible not only with all large cardinal axioms that we know, but arguably compatible with all large cardinal axioms that you can formulate in the language we use to formulate those axioms now. So one just has to prove this conjecture. Everything rests on this conjecture. If this conjecture is true, we have an ultimate L, solid mathematical reasons for believing that is ultimate L. If this conjecture is true, then this axiom gives you a robust view of the universe of sets. The only ambiguity are large cardinals. But that was always what Gödel wanted. Some vision or view of the universe of sets where the only ambiguity is what large cardinals exist. You must always have that ambiguity by Gödel's second incompleteness theorem. An advantage to this conception as opposed to L is it's well known that large cardinal axioms prove statements about L that you can't prove without them. So if you were living in L, you would see even arithmetic statements, even seemingly natural arithmetic statements true, but you would be unable to account for why they're true because your universe can't accommodate the large cardinals that are responsible for it. Ultimate L accommodates all large cardinals, so there can be no such statement about ultimate L. Anything that large cardinals prove about ultimate L, well, those large cardinals can exist in ultimate L. And so ultimate L can see the reason those statements are true. So in that sense, it becomes a very nice setting to do set theory. So the dream, if you will, is that this conjecture is true. And then finally, we have a setting to do set theory that's unencumbered by independence. Right now, if you try to do set theory, everything's independent. Very hard to build a rich structure theory when everything is independent. And this might provide that setting. On the flip side, once you're at this stage, this conjecture could just be false, in which case this whole program of ultimate enlargements doesn't work. And we're back to square one. We need an attempt 3. So that's it. Thank you.